Welcome, respiratory care students, to Elastic Properties of the Lung and the Chest Wall. This is part of Desjardins, Chapter 2, and we're on Part 3. Both the lungs and the chest wall each have their own elastic properties, and under normal conditions, each elastic system works against the other. That is, the chest wall has a natural tendency to move outward or to expand. This is a result of the bones of the thorax and its surrounding muscles. The lungs, on the other hand, have a natural tendency to move inward or collapse. This is due to the natural elastic properties of lung tissue. This lung-chest wall relationship is often compared to that of two springs working against each other. The chest wall works to spring outward. The lungs work to recoil inward. Clinically, the elastic forces of the lungs are routinely evaluated by measuring lung compliance. So what is lung compliance, or C sub L? So lung compliance is how readily elastic force of the lung accepts a volume of inspired air, or the air you breathe in. How easy is that? How much force does it take for you to take that breath in? Let's look at that. What is lung compliance really equal to? It's equal, if you were to figure it out with your calculator, it is equal to the change in lung volume, or delta V, per unit pressure change, or delta P. So delta V divided by delta P, the change in lung volume divided by the change in pressure. So I have a question for you. What formula is used to calculate lung compliance? We just saw it. Think about it a minute, and here's the answer. Delta V divided by delta P, or the change in volume divided by the change in pressure. Good job, everybody. It really doesn't matter whether the change in driving pressure is in the form of a positive or negative pressure. For example, if an individual generates a negative pleural pressure change of about 5 centimeters of water pressure during inspiration, and the lungs accept a new volume of a half a liter or 500 milliliters of gas, the compliance of the lungs would be expressed as 0.1 liter per centimeter of water, or if you used milliliters, 100 milliliters per centimeter of water. So I have a question for you. What clinical measurement is used to evaluate the elastic forces of the lungs? We just have been talking about it. You are absolutely correct. It is lung compliance. Great job, everybody. Normal volume pressure curve is shown in the graphic to the side. The curve shows that lung compliance progressively diminishes as lungs expand in response to increased volume. Please note, the greater volume change between 5 and 10 centimeters of water pressure for little tiny alveoli than the 30 to 35 centimeters of water pressure in the bigger alveoli. When lung compliance diminishes, the volume pressure curve shifts to the right. When lung compliance increases, the volume pressure curve shifts to the left. Pictured in blue in the middle is a normal volume pressure curve. So I want you to think about this. in what kind of disease states would compliance increase? If you said COPD, you're absolutely correct. What about when would compliance decrease? What kind of disease would cause a decrease in compliance? If you said ARDS, you are absolutely correct. Increase or overly compliant lungs? A great example is COPD. Decreased compliance or lungs that are very stiff and hard to move? ARDS. As mentioned previously, the chest wall has its own elastic properties, and these are caused by the bones of the thorax and the surrounding muscles. As a result, the chest wall works to offset the normal elastic properties of lungs. If unopposed, the normal compliance of both lungs and chest wall are about equal, at about 2.2 liters per centimeter of water. However, because the lungs are enclosed within the thorax and attached to the internal surface of the chest wall, the two elastic systems function as springs that naturally recoil away from each other. This action, in turn, decreases the compliance of each elastic system to about 1/2 of each of its parts, or 0.1 liters per centimeter of water, which, if you notice, is normal lung compliance. We've been talking about compliance, but let's talk about elastance, the ability to snap back into shape. Part of that is explained by Hooke's law. You can see in the picture a picture of the scientist that originally thought up this law. Hooke's law provides another way to explain compliance by describing physical properties of an elastic substance. This can be the elastic in your underwear, or a spring, or a lung. So what Hooke's law says is that when a truly elastic body, like a spring, is acted on by 1 unit of force, the elastic body will stretch 1 unit of length. When acted on by 2 units of force, it will stretch 2 units of length, and so forth, until it is stretched to the point where it is overstretched. Then it will quit having a 1-for-1 relationship, and the units of length for each unit of force will get smaller and smaller, until finally the spring is overstretched and it breaks. Let's look at this. Springs are all about elastance. Elastance is defined as a change in pressure per change in volume. If that looks familiar, it's because it's just the opposite of compliance, or the reciprocal. The lungs with a high compliance or greater ease of filling have a low elastance. Lungs with low compliance, or really stiff lungs, have a high elastance. Stiff lungs snap back into shape. Really compliant, overly compliant lungs do not snap back into shape very easily. Hooke's law states that when force exceeds elastic limits of a substance, ability of length to increase in response to force rapidly diminishes. Should the force continue to rise, the elastic substance will ultimately break. How do we apply Hooke's law to the lungs? Well, When applied to elastic properties of lungs, volume is substituted for length. Pressure is substituted for force. So you can see, at a pressure of 5 centimeters of water pressure, the volume is level. When the pressure in the lungs doubles, the volume in the lungs doubles. When the pressure in the lungs triples, the volume level triples. Until we quadruple or have 4 times the pressure in the lungs, then the volume level increases very little. And finally, at 25 centimeters of water pressure and 30, the volume level is beyond the elastic limit lung unit. This is the end of our time together, so I thank you very much for your time and your attention.